Hello, welcome to Vijay Biology Tutorials. So in the chapter hydrogen, now we are going to discuss about the topic hydrates. We see the dihydrogen under some conditions reacts with almost all elements and forms hydrates. Now we see these hydrates are binary compounds and hydrogen doesn't react with noble gases. The general form of hydrates is E. Let E is an element. Then hydrates can be expressed as EHX or EMHN, where M and X are stoichiometric coefficients. Now, these hydrates are divided into three types, that is, ionic or saline hydrates, covalent or molecular hydrates, metallic or non-stoichiometric hydrates. First, coming to ionic or saline hydrates, stoichiometric compounds of dihydrogen formed with most of highly electropositive element in character. So we see the most electropositive character is represented by elements of S block. Now that this is a hydrate which is ionic or saline hydrate. When ionic or saline hydrate react with water, gives us the resulting base and dihydrogen. But lithium hydrate, beryllium hydrate and boron hydrate are of covalent character because they are lightweight elements. When it comes to covalent or molecular hydrates, most of the p block elements react with the dihydrogen to form covalent or molecular hydrates. The electron deficient hydrates, boron belonging to p block, reacts with dihydrogen to form these covalent hydrates. Whereas, as we see before, these are the examples. We considered these examples as covalent character. These beryllium hydrate and lithium hydrate are considered as covalent molecular hydrates and electron deficient hydrates because even beryllium gains 2 electrons from hydrogen or shares 2 electrons with hydrogen. Beryllium does not attain its octet. Similarly, lithium also doesn't attain its octet. Now coming to electron precise octet, electron precise hydrates, which means they have sufficient number of electrons after forming a bond with hydrogen. In organic compounds, we observe most electron precise hydrates. CH4, the carbon valency is 4 and 4 hydrogens share single electron with one carbon and form CH4. In this way, the octet of carbon is satisfied and hydrogen is also satisfied. In this way, organic compounds are considered as electron precise hydrates. When we come to electron rich hydrates, these hydrates have electrons extra, which means after formation of water, the extra lone pairs are considered as extra electrons, such as when hydrogen shares 2 electrons with oxygen, there are still 2 lone pairs present in the oxygen. In such cases, they are called electron rich hydrates. Examples of these are H2O, NH3, hydrofluoric acid, and so on. Now coming to metallic and non-stoichiometric hydrates. These non-stoichiometric hydrates means they don't have a particular stoichiometric coefficient of reaction. So when we consider these examples, ytterbium hydrate, titanium hydrate and zirconium hydrate, see, in the previous case, we observe a specific whole number such as NH3 and here 2 hydrogens. But this is not a specific whole number, which is 2.55. As this is not a specific stoichiometric coefficient, these are set as non-stoichiometric hydrates. But as we know, D block and F block elements form non-stoichiometric hydrates by reacting with dihydrogen. When this dihydrogen reacts with the elements of 7, 8 and 9 groups in the periodic table, no hydrates are obtained. Even in the 6th B group, only chromium forms chromium hydrate. Now coming to PD and platinum, they accommodate very large capacity of dihydrogen. This property has high potential for hydrogen storage, which is an essential property for energy source. By this, we can create a lot of energy. Thank you for watching this video. Have a great day.